section 3.2 of the guided notes. And in this one, we're going to use some radical and rational exponent properties. The chapter begins with a discussion about rational and irrational numbers. A rational number is any number that can be written as the ratio of two numbers, A over B. And A and B have to be integers. Integers are, for example, -3, -2, -1, 0, 1, 2, 3, 4, ... Those are the integers. So a rational number can be written as any ratio of numbers, and example, 4 over 2 is the rational number 2. Likewise, any of these other numbers, just here's another example, 4 over 1 is the rational number 4, right? An integer divided by an integer equals another integer. But the irrational numbers is a number that is not rational. It goes on forever with no predictable pattern. Fun fact, the Egyptians learned about irrational numbers when they tried to determine the square root of 2. Another example of an irrational number is pi. Presently, pi is calculated to over 13 billion decimal places, and you don't have to write this down. This is just fun facts. NASA and the International Space Station use pi to 16 decimal places for navigation. But basically, pi is probably the most famous irrational number. Let's see. Complete the following addition table with both rational and irrational numbers combining like terms with when possible. So if I was adding negative pi and negative pi, I'd get negative 2 pi. This would be 7 minus pi, 1/4 minus pi, square root of 3 minus pi, negative square root of 3 minus pi. And this is all just experience writing all these different things. So you'll notice it almost treats particular ones almost like you're adding x's and y's. It treats them where there are terms that you can combine and terms that you can't combine. Now, the square root of 3, for example, does have a decimal number, but the decimal, believe it or not, is actually less precise than, right, you got the square root of 3. This is more precise than what you get in a calculator. Right, and if you type that in the calculator, it's like 1.732050808007. It just keeps going. Right, this is like an approximation. This is exact. And I would much rather take, write this than have to write this whole mess every time I used it in an operation. So, something to consider about the purpose of radical notation is technically it's probably less work. than writing out these numbers all the time. Right, if I add 1 root 3 and 1 root 3, that's going to be 2 root 3. And then this negative and this positive simply becomes 0. So hopefully this is just giving us tons and tons of practice, basically showing like terms and unlike terms. I'll give you a little bit of time to write all that down and fill in that grid. Now in this section, the sum of two rational numbers will always be a rational number. But the sum of a rational number and an irrational number will never be a rational number. And let's do like an example, right? 2 is rational and 4 is rational, and they equal another rational number that is 6. However, 2 is rational, but pi is irrational, and this will never be a rational number. That is, I will not be able to take this and express it it cannot be expressed as a ratio of integers. A over b. Right? You're never going to find two integers, one divided by the other, that equal this, because it's irrational. So sum of two irrational numbers will sometimes be a rational number. And I'm going to give you an example. The square root of 2 is irrational. But if I add it to the negative square root of 2, I will get the rational number 0. So sometimes you can add two irrational numbers and get a rational number. Here would be an example. Another example you've already seen, pi plus a negative pi, right? Make the rational number 0. So now let's dive into some properties of exponents. So if I have a to the m power times a to the n power, it winds up being that I can just add the exponents. And now let me give you a numerical example. Say I had 2 to the second power and it was multiplied by 2 to the third power. You'll notice 2, just like our a, has the same base, right? Boom goes the base. That's the base. This is going to equal 2 to the 2 plus 3 power, which is 2 to the 5th. So that is a property of exponents. It's called the product property. Interestingly enough, when I multiply things of similar base with different exponents, I can add the exponents together. The quotient property allows me, if I have the same base but different exponents, to subtract the exponents. And I'm going to give you a numerical example. If I have 3 to the 4th divided by 3 squared, this is the same thing as having 3 to the 4 minus 2. And 4 minus 2 is 2. So there you go. The power of a product property, if I have different bases and they're in parentheses raised to the power of n, that would be the same thing as having a to the n times b to the n. So let me give you an example right now. let's say I had 2 times x squared. Well, this is going to be equal to 2 squared times x squared, right? Because the 2 gets distributed in the exponent world. It is both 2 squared and x squared. Another way to think of it is, right, if 2x squared is basically 2x times 2x. What is that? 2 squared and x squared. So you wind up getting 4x squared. The power of quotient property likewise distributes if my bases are different. If I have a divided by b to the n power, that's the same as a to the n divided by b to the n. And let me give you another numerical example. If I have 3/5 raised to the third power, that's the same thing as saying 3 to the third divided by 5 to the third, right? And you're going to wind up with 9 over 125. It's also the same as this, right? 3/5 times 3/5 times 3/5, and you get the same thing. But you'll see how these various rules help us solve some of these things quickly without having to write them all out. And then if I have a raised to the power of m and surrounded by parentheses, that's raised to the power of n, then likewise I can multiply. Instead of adding exponents, now I'm multiplying exponents. So here's a numerical example. If I have 4 to the third times, let's see here. If I have 4 to the third, and it is raised to the second power, this is in essence 4 to the 3 times 2. And 4 to the 3 times 2 would be 4 to the 6th. So that's the power property. And I know just seeing them for the first time, it's going to take a little bit of practice, but that's part of what we have all those IXLs for. And we're going to be going through this on multiple worksheets and on HRW exercises. Now this table is basically going to multiply some rational and irrational numbers. The prior table you were doing was adding these things. Now we're going to multiply these things. And for instance, negative pi times negative pi is going to be pi squared. This would be negative 7 pi, negative 1/4 pi, 0, negative pi root 3, positive pi root 3, negative 7 pi, 49, 7/4, 0, 7 root 3 is how that would be written, negative 7 root 3, right? If I'm multiplying this and that, this is what we're getting in the box. Negative pi over 4, 7/4, 1/16, 0, root 3 over 4, negative root 3 over 4, 0, 0, 0, 0, 0, 0. This is all 0 as well. And let's see. Negative pi root 3, positive pi root 3, 7 root 3, negative 7 root 3, root 3 over 4, negative root 3 over 4. So more than enough practice. Here's an interesting one. When I have root 3 times root 3, 3. Root 3 times the negative root 3, negative 3. And here's negative 3 and 3. Let's give you a moment to do those. So here we go. The product of two rational numbers will always be rational. And write an example, 3 times 4 equals the rational number 12. I know this is rational because 12 can be written as a ratio of integers. There are many ways to write this as a ratio of integers. You could probably literally name an infinite ratio of integers to represent 12. But that's basically what makes it rational, is that two integers can be used to express it in a ratio. So here we go. The product of two irrational numbers will sometimes be rational. And I'll give you an example. The square root of 2 is irrational, but if I multiply it by the square root of 2, I get the rational number 2. And that's kind of an interesting product in and of itself. I mean, if you think about it, the square root of 2 is a number that goes on forever with no pattern that can be determined. And so basically, if I have this thing that goes on forever with no pattern that can be determined, multiplied by this by itself, you get something that can just be expressed by the ratio of two integers. So that's kind of neat. It goes from basically an infinitely complex number, in a sense, by its irrationalness, to very simply 2. The product of a rational number and an irrational number will never be rational. Never. So if I have the rational number 2 and it's multiplied by the irrational square root of 2, this 2 square root 2 is irrational. That simply means I cannot express it like I can 12 as a ratio of two integers. So now let's try a few examples. The examples in the notes, there's not too many because we have so many that we're doing in the worksheet and in HRW, but let's give this a go. So if I have x and y to the 9th, right, this is our power property. So you do, in essence, have essentially the cube root of x to the 9th and y to the 9th. And then you also have essentially that you could rewrite these, that this is basically x to the 9 over 3 and y to the 9 over 3. And that hopefully leads you to the conclusion that, what is 9 divided by 3? That's going to be x to the 3rd and y to the 3rd. And that's basically just applying several different rules of exponents to get to that conclusion. If you'd rather, this is essentially 9 x's. So there's 4, 5, 6, 7, 8, 9. So you basically have x, 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 x. Now I think this way is a little more complicated, but maybe it will help you conceptually. How many x's is that? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9 x's. And cube root, you are looking for sets of 3 numbers, because it's the cube root. So I'm looking for sets of 3. Well, there is one set of 3. There is another set of 3. There is another set of 3. So coming out of this cube root, it's going to be x and 3 of them. 1, 2, 3 sets. And you can see very, very easily that y is basically to the 9th as well. And so you would wind up likewise with 3 sets of y. So I hope that helps seeing both ways. Now let's look at this example. Right, this right here is in essence y to the 4 over 4 power. What is 4 divided by 4? Simply y, right? Like this part is just equal to y to the first power. So what you have is x squared times y times y. And when it's like this, right, we basically add the two exponents. So this is going to be x squared to the y, 1 plus 1. In other words, x squared, y squared. And here we go, the fifth root of x. This is like x to the 1/5. And that's the square root of x. So this is like x to the 1/2. And now we can just basically add these two together. This is going to be x to the 1/5 plus 1/2. They have the same base. We can just add the exponents. 1/5 is like 2/10, and 1/2 is like 5/10. So this is going to be x to the 7/10. And unfortunately for you, maybe, is, a problem like this probably doesn't have a solution on the calculator. This is all, in the gray matter. This is like your brain. And your brain can do these, your calculator not so much. I'm not that familiar with Photomath, but I'm not sure if it'll do these either. But you could try. But I don't know if it's that sophisticated, but maybe. So let's see here. Let's do this next one. So this whole mess looks kind of complicated, but if you break it down into simpler terms, right, this is going to be essentially x to the 8 over 4. And on top of that, it's going to be x to the 6 over 4. And you'll remember in our rule, right, we could just basically subtract these two things because we have the same base. So this is going to be x to the 8/4 minus 6/4. And you should wind up where this is x to the 2/4, which is x to the 1/2. And that can also be written like that. So there's a couple examples. We're doing lots more because there's just so many different problems with stuff like this. But this section is very important. It will build into something we're going to do later in the year. And hopefully this is starting to make some sense.